The next type of transformation that we're going to discuss is translation. Okay, please don't mix up transformation and translation. Okay, they both have the trans in the beginning, but a transformation is any type of change to the graph. A translation is a very, very specific type of transformation. So translation moves the graph. So we talked about in the last lecture that we have different types of transformations. So the first type of transformation we talked about was reflection, and we said that that changes the orientation of the graph. Here we have translation that moves the location of the graph. And then we also talked about non-rigid transformations and rigid transformations. So this is rigid because the shape does not change. Okay, we're just changing where it is on the coordinate plane, but we're not changing what it looks like. So this is a rigid transformation. And there are 4 ways that we can translate a graph, that we can move a graph. The 4 ways are up, down, left, and right. Any other type of movement, like on a diagonal, that's a combination of up and right, or up and left, or down and right, and down and left. So we're only going to look at each one individually, and then we can combine it. Okay, and we can even combine it with reflections now that we've done reflections, because you can take a graph and translate it and reflect it. So you can do 2 transformations simultaneously. So let's start with the up and down. Okay, so this is the first type of translation that we have. And if we're going up, think about, sorry about that. Let's think about a simple graph like y equals x squared. So notice I'm not using linear all that much. That's because linear could be a little bit more difficult to see clearly the different types of reflection. Okay, so whereas quadratic, it's simple to see. So if we want to move a graph up, okay, we can do the same thing that we do with points. We could say, well, how do we move a point up? In order to move a point up, we add to the y value. Well, that's the same thing that we're going to do here. We're going to add to the y value. And if you remember, the y value is the whole function. If this is f of x equals x squared, the y value is x squared. So if we add 1, we've moved this graph up 1. So here's the original graph, x squared. And we've just moved it up. That's all that we've done. Okay, so let's go and write that down. So to move a graph up, we want to add to the y value. So f of x, so let's say that we move up by c units. Just so that we have something specific. So we're adding c to f of x. So f of x becomes f of x plus c. Okay, so let's say that c is equal to 3. That's a 3, not an 8. Sometimes these 3s come out looking like 8s. It's just, again, it's just the pen and the paper I'm working with. Okay, so it's c is equal to 3. Let's take different functions, okay? So let's take we'll just take a bunch of different types of functions. So we might use ones that are a little bit different than the ones that you saw in the previous lecture. So let's say that we have f of x is equal to, we'll start with a linear, 2x plus 6, okay? Then we'll do f of x equals 3x squared plus 7x, so that would be like a polynomial function. We'll do f of x is equal to 7 to the x minus 4, and we'll leave it like that. Let's do f of x is equal to the log of 6x plus 8, and we'll put in an absolute value function as well. Absolute value of 6x minus 5. Okay, so for each of these, we're going to move it up by 3 units. And we'll talk about, there's a notation for this, but we'll talk about that afterwards, because the notation takes into account up and down and left and right simultaneously. So here, this would be f of x plus 3. Okay, we're adding 3 to our y, so the f of x plus 3 is the new notation. So f of x plus 3 here is just 2x plus 6. And then just like we tacked on a negative sign, we're just going to tack on a plus 3. And we're putting it at the very end, so we actually never need parentheses. But if you want to, again, just to be consistent, you can always use parentheses. You just never need them because you're just tacking on a plus 3, and it does not change the order of operations. So if we take this and we go up 3, it's the same thing. Each time, you're just tacking on a plus 3 to the end. And I'm doing it with so many different functions. 1, because I want you to see it over and over again. And 2, because I want you to see that it looks exactly the same no matter what type of function it is. So we have an exponential function here. It doesn't matter. We still just tack on a plus 3. Here we have a logarithmic. And again, it doesn't matter. We just tack on a plus 3 to the end. And finally, we have an absolute value function. And again, we just tack on a plus 3 to the end. Okay, so a couple of things to note. Here, we just put in a plus 3. Here we put in a plus 3 and we can simplify. This becomes 2x plus 9. We don't have to worry about parentheses or anything. Okay, here that plus 3, it's not a like term, so we can't add it. So we just leave it like this. Same thing over here. Over here, you're taking the log of 6x plus 8. Now 6x plus 8 is in parentheses. That is the only thing that you are taking the log of. So you cannot combine the plus 8 and the plus 3. You're not taking a log here. Okay, so that's just something to note. These can't be combined because you're not taking the log of 3. And the same thing is true here. These are not like terms. You can't combine them because that minus 5 is inside the absolute value, but the plus 3 is not. So you really can't combine these. So just a note as to what you can simplify and what you can't. Okay. Now this is up. And if you know up, then you know down. It's just automatic, okay? So let's do down. And I'm sure a lot of you are already saying, okay, we know what down is. So in down, instead of adding to the y value, we subtract from the y value. So if we move down by c units, subtract c from f of x, and f of x becomes f of x minus c. So we're going to do the same thing. We're going to say, okay, let's suppose that c is equal to 3. And if we take the same functions, so we'll do the same exact ones, f of x equals 2x plus 6. These are, I didn't do a rational function, so I'll replace, so we'll add in a reciprocal function in there. Again, we're just doing so many so that you can see all of the different types of functions that you can do this with. It works the same way in every single function. It never changes, whether it's quadratic, any sort of polynomial function, any sort of logarithmic function, any exponential function, any reciprocal function. It's always going to be the same. I just did the same thing over again. So this is 7 to the x minus 4. This is f of x equals the log of 6x plus 8. Here we have f of x is equal to the absolute value of 6x minus 5. And we'll add in one here that's reciprocal. We'll just do f of x equals x plus 2 over x squared minus 8. Okay. And again, all we have to do with each of these is subtract 3. So we're going down by 3. And this says, okay, f of x is equal to 2x plus 6 minus 3. So we're just tacking on a negative 3. We're not multiplying. We actually are subtracting. Okay. And it's same thing here. Every place where you saw a plus 3 before, now you're seeing a minus 3. So it's 3x squared plus 7x minus 3. Then this is going to be 7. I'm sorry, these should be minus 3. So I'm going to just erase this. It should be f of x minus 3. I don't want to confuse you. Okay. So we have f of x minus 3. This is f of x minus 3. Here again, f of x minus 3 is 7 to the x minus 6. And just be careful about your handwriting here. The minus 3 should be clearly not part of the exponent. So this is a case where putting parentheses around the exponent might be helpful to you. And I wrote x minus 4, x minus 6 again. X minus 4. This is where it might be helpful to put parentheses around the exponent just so that it's clear to everybody that this minus 3 is not actually part of the exponent. Okay? Then we have f of x is equal to the log of 6x plus 8 minus 3. This should be f of x minus 3. It's a little bit later in the day, so I'm a little bit more tired, which is why I'm making these mistakes. Sorry about that. F of x minus 3 is the log of 6x plus 8 minus 3. So notice we're changing the notation. The reason why we changed the notation from f of x to f of x minus 3 is for 2 reasons. One, it tells us what we've done to f of x, okay? And 2, it's like a set of instructions for somebody else, okay? These functions are not both f of x, right? F of x is log of 6x plus 8. It's not log of 6x plus 8 minus 3. We don't want it to appear that these functions are the same. So that's why we have to put in f of x minus 3. It tells us what to do, and it tells us the difference between these two functions. So f of x minus 3 here is the absolute value of 6x minus 5. Minus 3, and again, you can't combine those. Here, it's x plus 2 over x squared minus 8. And then it's just minus 3. Okay. Okay, so that's up and down. So now we have left and right. And it seems like, oh, this can be so clear. There's one caveat about going left and right. And we'll talk about it, but I'm first going to give you what you do, and then we'll talk about why there's this exception, why there's this difference or surprising thing that goes in there. So let's start with going to the right. Okay, so here's the big difference. When we take a point and we move it to the right, okay? I'm gonna get rid of this. If we take a point and we move it to the right, we would add. But when we're taking a whole function and we're moving it to the right, we're actually going to subtract. And this is the big difference, okay? So when we go to the right, this is a horizontal change, okay? Horizontal change means that we're affecting the x. Going right or left changes things horizontally. The x-axis is horizontal, so that's how we remember what's going on here. So a change to the right says not that we're adding to x, but that we're subtracting from x. So this is the big difference. And we're gonna explain this, but I'm gonna do it after we do left and right. So if we move right by 3 units, or let's say by c units originally, we subtract c from x. Okay, in other words, f of x becomes f of x minus c. So let's do the same thing that we did with up and down. Let's say that suppose we go to the right by 3. In other words, c is equal to 3. Okay. Let's take our same functions just so that we're using them again and you can see the difference. So we're going to take the same 6 functions. F of x is equal to 2x plus 6. F of x is equal to 3x squared plus 7. Plus 7x. F of x is equal to 7 to the x minus 4. F of x is equal to the log of 6x plus 8. F of x is equal to the absolute value of 6x minus 5. And an f of x, that's an absolute value sign. And an f of x is equal to x plus 2 over x squared. Okay, so the computer crashed right around here, so you're going to see a lot of writing that just appeared. So I'm just going to go through it, okay? So we said when we go to the right, we subtract from the x. And if we move right by c units, then we subtract c from x, right? It's the opposite of what we might think. So f of x becomes f of x minus c. So we said, okay, so suppose we go right by 3, okay? So if we go to the right by 3, then what we're doing is we're saying we're subtracting 3 from x. So it's the opposite. We might think that we would add c to x, but we're actually subtracting, okay? So here, we have f of x minus 3. This is just like composition of functions. We replace our x with an x minus 3. So 2 times x minus 3 plus 6. We can simplify, okay? So we can distribute the 2. When we distribute the 2, we get 2 minus 6 plus 6, which just becomes 2x. Now, I'm not going to worry about simplifying all of these other functions. Just the idea is every x gets replaced by an x minus 3. So we have 3 times x minus 3 squared plus 7 times x minus 3. Then over here, this was 7 to the x minus 4, so it becomes 7 to the x minus 3 minus 4. So we just took our x and replaced it with x minus 3. In this one, f of x minus 3 is the log of 6 times x minus 3 plus 8. So again, our x just got replaced with an x minus 3. It was a replacement, okay? Just like in composition of functions. X got replaced by x minus 3. Same thing in the absolute value function. The x gets replaced by x minus 3. In this function, our reciprocal function, x and x, both of these get replaced. We have an x minus 3 here, and we have an x minus 3 in the bottom, okay? So that's to go to the right. Now, not surprisingly, to go to the left is exactly the same, okay? Just ignore the bottom of the page for now. Instead of subtracting, we add to the x value. So again, it's the opposite of what we think it is, okay? So if we move to the left by c units, we add c to x. So f of x is going to become f of x plus c. So again, let's suppose that c is equal to 3. So we don't have to do every function because we already know how this works. Every x gets replaced by an x plus 3, okay, when we go to the left. So here we have 3x squared plus 7x. So we have 3 and then our x and our x, right? So we have our two x's, and what do they get replaced by? They get replaced by x plus 3's. Same thing here. We have x in our exponent. It becomes an x plus 3 in the exponent over here. Here we have 6 times x minus 5. Here we have 6 times x plus 3 minus 5. And then I also put in the reciprocal function. Our x in the numerator gets replaced by an x plus 3. Our x squared gets replaced by an x plus 3 squared. So it works the same for every function. But remember, when we go to the left, we add. When we go to the right, we subtract. Okay. So why do we add to x when we go to the left? Okay. This is a little bit harder to explain if you can't really see what's going on. I usually do a physical demonstration for this. But I want you to imagine that somebody comes up to the front of the room, okay? And they're, let's say, 5 feet, okay? So this is their height. Then we take somebody, and what we're doing is we're moving this person to the left, okay? Now, in order to do that, we're going to take a new person, just because we want to show you what it looks like. So we take a new person, and we make them go 3 spaces to the left. But now what they have to do is they have to figure out, well, how tall do they need to be? And in order to figure out how tall they need to be, they need to look at the person who's over here. And that person is to the right of them. So this person is moving to the left, but in order to figure out their height, which is the y value, they have to actually look to the right. So that's where the f of x plus 3 comes from. Because the x value that we're looking at is really the x value over here, which is x plus 3, okay? So it's not about where we came from, okay? It's not about where we're going. It's not about the fact that we're going to the left. It's about the fact that we came from the right. So let's just look at this on a graph. Okay, so here's x squared, and let's move x squared 3 units to the left. Okay, and we already know that that means that the x gets replaced by x plus 3. And I want you to see what's going on here, okay? If we want to figure out the y value over here, okay, in order to do that, we have to look at the y value that it was over here, because these two y values are the same. So on the new function we call this x, okay, what we're doing in order to figure out what this should be, we can't look at f of x because f of x is down here, right? That's not moving it. What we have to do is we have to look at the y value that's at x plus 3. So we can't look at the y value at x equals -1. In order to figure out what this y value must be, we have to look at the y value that was 3 spaces to the right. Okay, so same thing here. If we want to figure out what this y value should be at -5, we have to look at what the y value was at -2 on the red function. Okay, so if this function is f of x, okay, over here, it's not, our y value is not f of x, because f of x on the red graph is way up through there. Okay, what we have to do is we have to look at, okay, if I want to figure out what my y value is, I have to figure out what the y value was on the function 3 units to the right. So it's about where we came from, not where we're going. If we move this to the right instead, it's the same thing. If I want to figure out what my y value should be here, I can't use f of x, because that's over here. I can't use f of x plus 3, because that's going to be way up through here. The y value over here is equivalent to what the y value was 3 spaces to the left of here on the red function. So 3 spaces to the left of here on the red function is x minus 3, right? We're looking at f of x minus 3. So it's about where we come from, not where we're going, okay? So that's where that concept comes from. Okay, so when we go to the left, we add, and when we go to the right, we subtract. Okay, so that's all of translation. Let's kind of put it together, okay? So first of all, there's a notation to this. I just need to make sure this doesn't crash. I apologize if you're hearing my frustrations. My recorder just disappeared, that's why. Okay. Sorry about that. I needed to make sure that it's still recording. It is still recording. Okay. So I apologize for you hearing all of my frustration. This is the 4th time my computer has crashed while I have done this video. So, okay. So in terms of notation, how do we translate a graph? How do we show it? So with reflection, it was like the large R and then the x-axis, right? Or the large R and then the y-axis as a subscript. For translation, it's T, and then you're going to see 2 numbers, a C, comma D. So here, it's the opposite of what it is in the function. So if our C is greater than 0, then we're saying that we're actually going to the right. So if C is positive, we're going to the right by C. And if C is negative, then we're going to the left by C. The D is more clear because, excuse me, it's consistent with our function notation. So if D is greater than 0, we go up by D. And if D is less than 0, then we go down by D. So let's take an example. Let's say that we have f of x equals 2x squared. And we have t 3 comma negative 5. So this is positive, which means that we're going to the right. And the 5 is negative, so it means that we're going down. So in function notation, what we're doing is we're saying that we're doing f of x minus 3 minus 5. That's what it looks like. I'm going to rewrite this 3. I don't know why the 3 is coming out that way. Okay. So remember, going to the right, we subtract. Even though this is positive, in the actual function, we subtract. And we can go down by 5 at the same time. Okay. So what this is saying is replace your x with x minus 3, and then tack on a minus 5 at the end. So what does this become? 2 Then our x becomes x minus 3. Our x minus 3 was squared. And then we tack on a minus 5. Let's say, for instance, that we have f of x equals the log of 3x plus 1. Okay, and we're going to translate -2, 4. Okay, well, what does this tell us? The -2 says that we're going to the left. And the +4 says we're going up. So we're going left 2 and up 4. So what does that mean in our function notation? Well, going to the left says that we add. So it becomes x plus 2. Okay, so notice you're switching the sign. If this is negative, then inside the function it's positive. And we're going up 4, so we tack on a plus. So it's only the opposite for the x values. Okay, for the y values, it's the same. Okay, well, what does this translate to in the function? This says replace our x with x plus 2 and tack on a plus 4. So in the actual function, what does that mean? Well, log x now becomes x plus 2. Don't forget about that plus 1. So it's easy to forget about these extra things, right? It's easy to forget about that. Don't forget about those. And now we just tack on a plus 4. So you're kind of doing one at a time. You're first moving it to the left, and then you're adding 4. Okay, let's take another one. Let's say that we have f of x equals 3 to the 6x minus 4. Okay, and now we're going to translate this. Let's do it as 1 comma minus 6. Okay, so what does this mean? Well, the 1 means that we're going to the right. And the minus 6 means that we're going down. So what does this mean in terms of function notation? Well, in terms of function notation, going to the right by 1 means we subtract 1 from x. And then down 6 means that we just tack on a minus 6 at the end. So we have 3, then we have a 6, and x is getting replaced by x minus 1. Don't forget about the minus 4. And then we're subtracting 6. Okay, and what I'm going to do is I'm going to add a parentheses around this. And the only reason I'm adding a parentheses is just so that it's really clear that this minus 6 is not part of the exponent. Okay, so we take the whole function and we just do minus 6. Okay, I'm gonna stop there. 1, because my computer is causing me so many problems, and 2, because if we're gonna combine transformations, we may as well do it when we have the third transformation done. So this is translation, and then in the next lecture we'll do dilation, and then we'll combine all of the different types of transformations together. So we'll do a function where maybe we reflect it and we dilate it, or we dilate it and we translate it, or we reflect and we translate. Okay, so we'll sort of combine everything in the next one. But you can see it works the same way as every other function, and then we can do multiple translations at the same time. So when we go to the right by 1 and down 6, let's just do it with this one. 3 to the 6x minus 4. I think that you should be able to see it in this window. Just so that you see how it looks. So this is 3 to the 6x minus 4. And then if we take this and we translate it, so we're going to the right by 1 and down 6. So now, To the right 1 says replace x with x minus 1. Okay, and I'm going to add in the extra parentheses there. And then we're going to subtract 6 from the whole thing. So you can see we moved. I just want to check that I didn't mess anything up. So this moves it to the right by 1, and it moves it so you can sort of see where it turns. Okay, so if you look at where it turns over here, it's turning it. This one is probably not the best example because you're really looking at the change here. And if you're moving to the right by 1, that equivalent change is at 1. So you can see right before it starts turning, it's at 0 on this graph. And over here, right before it starts turning, it's at 1. And then we're moving the whole function down by 6. Okay. If we take the 2x squared, which might be a little bit easier to see. This one, if we look back at the notes, we translated it 3 to the right and 5 down. So it became 2 times x minus 3 squared. And then minus 5 because we went down by 5. And you can see this from the vertex that we went to the right by 3, right? And then we went down 5. That's what happened to the vertex. So we're looking at very specific points to see, oh yeah, we actually did translate it in this way. And this is like the translation on the diagonal that we were talking about, that it's just a combination of going, in this case, right and down. In another case, it might be up and to the left. Okay. Okay, so that's it for today. And I apologize because it's going to take me a minute to get this to stop recording. So stop watching now because it's over now. -8.